what up, everybody? Mr. Herr here on this Thursday morning. Hopefully everyone's doing super well. Sorry I couldn't be there to wish you a happy St. Patrick's Day yesterday. Hopefully that went well for you. And hopefully the tests you dominated. I'm going to be grading those today. Hopefully they'll be in the system somewhere right around second period. So hopefully you'll be getting a positive update from me. We'll talk about them and go over them most likely on Monday. And we'll go from there. Today we're going to try and start T distributions through YouTube. I know that's going to be tricky. I know it's going to take a little bit of maybe rewinding and rewatching this video. Please be willing to do that for Mr. Hamilton's sake as well as for everybody else. That way we can hit the ground running when I get back. So yeah, without further ado, let's do this thing. Sorry about the spring, ladies and gentlemen. My bad, algebra in the way. If you wouldn't mind, flip to Chapter 10, Lesson 3 in your booklet. I do owe you an apology. It's right after page 98 and 99. There's a reason that this book is a rough draft, because when you flip the page, it doesn't say page 100. Totally my bad. Hopefully you understand where I'm coming from. All right, so give you a moment to do that. While you're doing that, hopefully you received a new chart called a T distribution. Okay. T distribution chart looks an awful lot like this. We'll quickly go over how to read it. It's not hard, promise. We'll get through it. Start with the stutter. Okay. When we look at this formula, it honestly looks very familiar to what we've been doing. N is still the sample size. What S is, it's the standard deviation, but it's the standard deviation from a sample. If you're saying, what do you mean, old man? Up until this point, we've been working with population standard deviation, which is that sigma. It looks like a circle with a tail. But oftentimes, we don't know the population standard deviation. So we have to, helps if you have an L in there, we have to have a standard deviation from a sample. Don't worry, we'll talk through it. Similarly, what this is, ladies and gentlemen, this is our sample mean. Now, don't feel as though you have to flip back, but I do just want to show you that this looks uber similar to our formula on page 92. The two differences are we don't have the population standard deviation, we have the sample, and we're going to use that T chart. You might say, oh man, why are we using a new chart? Because of the sample standard deviation. Because we don't have the population standard deviation, we can't use our normal Z chart. The rest, though, is pretty similar. So, very quickly, for a simple random sample of 40 2007 Ford Mustangs, the sample mean gas mileage was 20 miles per gallon with a sample standard deviation of 1.5. So my sample mean is 20 mpg. The sample deviation, that's my S value, that's 1.5 miles per gallon. There were 40 Mustangs in the sample. Now, here's a new part. We have something called degrees, and sorry for being low on the video, degrees of freedom. That is abbreviated as DF, often with a lowercase f. Sorry, you know my lowercase handwriting is abysmal. What degrees of freedom is, it's how we look things up on our chart. It is always one less than our sample size. So if you're saying, what do you mean, old man? The quote-unquote formula, although you'll never really write it out, is always the sample size minus 1. In this case, because we have a sample size of 40, our degrees of freedom is 39. Okay? You might say, oh man, how does that apply? I'm going to show you here in a moment. So let's set up part of our formula and then we'll go. X bar plus or minus T alpha over 2. Well, in this case, X bar is 20. I don't know that T alpha over 2 just yet, but I do know my standard deviation. It's 1.5 over the square root of 40. Okay. Now let's talk about how to look up this T alpha over 2. My 90% confidence, okay, along with my degrees of freedom, tell me how to look this thing up. Hey, just FYI, and this might be a little out there, especially because we're doing it through YouTube. You might have to rewatch this. If we have 90% confidence, that means it's the middle 90%. Okay? That's what we're talking about. If it's the middle 90%, well, what value is left in this tail and that tail? You take the leftover 10% and you cut it in half. That means 5% is below, 5% is above. You know you're right if it adds up to 100. Certainly it does. Okay. Now, this 5%, this is what drives. 5% as a decimal is 0.5. Let's talk about, or excuse me, 0.05. Sorry for the stutter. Let's talk about how to use that. Grab our T-chart. Okay. And if you look up top here on our T-chart, there are all these decimal points. Okay. Well, we needed our decimal point to be 0.05 because of the way that this chart is set up. This chart is different. It tells us what's above our T value. So we want 0.05, and then this DF, this tells us degrees of freedom. So hopefully I can get all this on screen, maybe not. Here's my column I'm going to use, and I'm going to come all the way down to degrees of freedom 39. Okay? 39 degrees of freedom, one less than our sample size, and then I go over to 0.05, that column. For this particular problem, I'm going to use the alpha value of 1.685 because it was 39 degrees of freedom with an alpha of 0.05. Okay. You know how to run this, all right? You type, you go, you give me an interval. In the interest of time, I'm watching the clock tick-tock. I'm at 7 minutes and 30 seconds. I got to keep moving. Okay. From there we go. Now, you might say, Mr. Herr, is that it? Well, in general, yes, but on the other page, we take it a little bit farther. Okay. We're going to use that same confidence interval with a hypothesis. Let's look here very quickly. In 2001, the mean household expenditure for energy was $1,493. An economist, sorry for the stutter, wanted to know whether this amount had changed significantly. So this person thinks that the new mean is not equal to 1,493 because they think it has changed significantly. That means the original mean is that it is 1,493. We're going to use this here in a minute. Trust me, let's keep going. In a random sample of 35 households, so that's my N, he found the sample mean, it says the mean expenditure should be sample mean, to be $1,618. With a sample standard deviation to be 321. Construct a 95% confidence interval about the mean energy. And I'm watching the clock. I know I need to get moving. So 95% is in the middle. Okay. That means 5% is left over, but it's not 5% here, 5% there. We have to cut it in half. That means this is 2.5%. Above and below. Well, what's that as a decimal? Move your decimal 2 spots to the left. That's 0.025. That's going to be huge. You know what else is going to be huge? Something we haven't figured out just yet in this problem is our degrees of freedom. If we have a sample size of 35, degrees of freedom is 1 less than that amount. That means our degrees of freedom will be 34. So my formula looks an awful lot like this. If you're saying, oh man, where are you getting this formula? It's literally on the previous page. Okay, let's substitute and go. 1,618, that's my sample mean. I don't know my T alpha over 2 yet. I have 321 divided by the sample, or excuse me, the square root of the sample size. How do we look this up though? We use 0.025, that's along top, boom. And we had degrees of freedom was 34. So I go all the way down to 34. And it sure looks like my T alpha over 2 value will be 2.032. Okay? I'm going to throw this in here. You run this confidence interval. If this number is in the confidence interval, you do not reject. If this number is outside the confidence interval, you do reject. Just like what we did before. Try to go as fast as I could. Good luck today. And the worksheet's pretty apparent. Peace.